All right, let's get started. Hello and welcome everyone to the seventh week of interactive live sessions for the course on fluid dynamics and turbomachines. This course is being offered by NPTEL. It's being taught by Professor Shamit Bakshi and Professor Dhiman Chatterjee, both from the Department of Mechanical Engineering at IIT Madras. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. So, like every other week, we shall be solving some problems together and having discussions regarding everything and anything related to the course. So, without any further ado, let's get started. So, week 7, our discussions have been focused on the uh, understanding the components and functioning and performance of hydraulic machines, hydraulic turbo machines. Uh, on the one side, we had uh, hydro pumps, meaning pumps which are used to raise the pressure and deliver water. Mostly, the most common application of these pumps are for water supply and delivery, but there's a huge another huge application area in which in the industries where there's chemicals and other stuff being uh, pumped using such pumps. And on the other side, we learned about the performance of turbines and mostly focusing on hydro turbines or water turbines. And we also briefly touched upon the problems of cavitation and how to avoid them. Okay, so with that, let us get started. So here's the, sorry, here's the first question of today's session, which is asking us which of the following turbines is best suited for high head and low discharge. So high head meaning the H is available is high, but the flow rate is low. So in that case, which type of a turbine is best suited? Meaning, uh, for this application, it would have a high efficiency. That's the that's what is meant by best suited. Suitability is under these set of conditions, which turbine would have a high operational efficiency. Is it option A Pelton turbine? Is it option B, a Francis turbine? Is it option C, a Kaplan turbine? Or is it option D, a propeller turbine? Which of the following turbines is best suited for high head and low discharge applications? Is it option A Pelton turbine? Is it option B, a Francis turbine? Is it option C, a Kaplan turbine? Or is it option D, a propeller turbine? These are different kinds of turbines, and you have to pick whichever has the best suitability or highest efficiency under conditions where there's a high head available, meaning there's a high uh, pressure flowing fluid coming maybe from a very big height. So the head is not the problem, but the total volume flow rate is limited. This is actually very common in hilly regions where there are these new rivers being formed out of melting ice caps, and they eventually join with other bodies of water, and they become big rivers with a high flow rate. But there are small streams, and especially near waterfalls, where there's a limited amount of water, limited volume of water, which comes with a very high velocity coming from a very high, you know, height difference, maybe from a cliff or some other uh, geophysical uh, structure. So there's water coming from a very big height, but the total volume is limited. In that case, if you want to use a turbine to generate electricity using the water's energy, how do you do that? Do you pick a Pelton turbine for that, a Francis turbine, a Kaplan turbine, or a propeller turbine? So let's take a look at the solution. It's actually a Pelton turbine because it's an impulse type turbine, whereas the others are reaction type. So this is an impulse type turbine, whereas these ones are reaction type. So when head is high and Q is low, then it's these impulse turbines which are more suited for the application because they have uh, high efficiency only under these set of conditions. Whereas reaction turbines are better when the H is limited, but there's a high volume of water flowing through it. Actually, if you push this really far, then axial turbines like Kaplan and propeller would become more efficient or best suited under those conditions where there's very little H available, but there's a lot of Q available. All right, let's move along. We'll move on to question number 2 now, which is asking us that the main function of a draft tube in a reaction turbine is to do what? Is it option A, enable installation of the turbine above TRL, and the full form of this abbreviation TRL is tail race level. Tail race level. So that's option A. Then option B is saying that it is to decrease the outlet velocity. Option C says that the main function is to remove or prevent cavitation. And option D is both A and B. So question number 2 of today's session is asking us what is the main function of a draft tube in a reaction turbine. So let's say I have a turbine like this. This is just for visual representation. Right? There's a reaction turbine, then maybe this is the outlet of it, and you attach a very big tube to it before letting it out on any reservoir or body of water, which is called the tail race level, by the way. So this is what is the TRL, and this is the draft tube. And here's our reaction turbine. Is my video frozen for some reason? Let me check. I'm trying to turn it off and back on again. There seems to be some kind of an error. Let me rejoin. It's still not working. My video is not coming for some reason. Okay, anyway, let's just carry on with the class. So go back to sharing. Okay, there seems to be a lot of issues. I'll just move out of this. Is it all allowed anyway? Hey, I did allow these. It's all allowed. I think was working fine. I don't know what happened. No permissions given. About I try to join from another account. Mm, there is some serious issue going on here. Trying to get in. Okay, I'll just record this in a different way then maybe. Or what do I do? Let's try switching accounts. No, let's not do that. I won't be able to get in. Just present. Mm, Let's try incognito mode. Does this help? Let's create another meeting. I think it's some problem with Google Meet itself that's going on. Okay, let's try something else then. Mhm. Okay, so there's been some technical issues. So anyway, we would carry on like this right now. So I hope you can see my screen, and if I make some changes, that's also visible, right? Yeah. So coming back to question number two, this would be the correct solution. So basically, both the statements given in options A and B are correct. So statement A being to enable the installation of the turbine above the tail race level, that's true because the end of the draft tube is at, or the exit of the draft tube is at an ambient pressure or atmospheric pressure, where and due to the shape of the diverging shape of the draft tube, it can enable lower pressure at the entry point of the draft tube, which is also the exit point of the turbine, therefore enabling a higher pressure difference across the turbine so that more work can be uh, extracted from the water that's coming in. And that's so ultimately what that allows us to do is to uh, install the turbine at some height even above the TRL without sacrificing this additional bit of work that we can extract out of the turbine, out of the water. And the second function is to reduce the outlet velocity, which is actually kinetic energy of the water, which is not getting used or not getting extracted by the turbine to generate useful work. So draft tube really helps us with both of these purposes. So both A and B should be correct, and therefore option D should have been the correct choice instead of anything else. All right, so let's move on. We'll move on to question number three now, which is asking us that cavitation in hydraulic pumps primarily occurs when option A, outlet pressure is less than vapor pressure, option B, inlet pressure is less than vapor pressure, option C, flow rate is very low, or is it option D, when efficiency is very high? So, when does cavitation happen in hydraulic pumps? Is it when option A, the outlet pressure of the pump is less than the vapor pressure? Is it option B, the inlet pressure is less than the vapor pressure? Is it option C, the flow rate is very high, sorry, the flow rate is very low? Or is it option D, when the efficiency is very high? All right, let's take a look at the solution. It's actually option B, when the inlet pressure is less than vapor pressure. So basically, the location really doesn't matter. Wherever the pressure of the fluid drops below the vapor pressure, cavitation, there's a high chance of cavitation happening. But in a pumping system, so when there's some piping which is bringing it to the pump, and then it's being carried somewhere else, in this whole region, the lowest pressure happens at the eye of the pump, or near the inlet of the pump. So which is where it's sucking in uh, more fluid from the source, from the from the reservoir side. And this is where the lowest pressure happens, and therefore uh, the highest chance of that pressure going below vapor pressure is there. And as a result, cavitation also has the highest chance of occurring near the inlet of the pump. Okay, hope that's clear. Let's move along. So we'll move on to question number 4 now, which is asking us that for a Pelton wheel, so a Pelton turbine is also sometimes called as a Pelton wheel. So for a Pelton wheel, the ratio of the jet diameter to the wheel diameter is generally what? So, you have a Pelton turbine like this. I'm drawing one bucket, and there's this nozzle that you have, and this is the fluid jet that comes out. So let's say this diameter of this jet is dj, whereas the diameter of the entire Pelton wheel runner, that is capital D. So the question is, what is this ratio of this jet diameter to the wheel diameter? Is it option A, 1 is to 12, 1 is option B, 1 is to 22, option C, 1 is to 2, or is it option D, 1 is to 50? So these are, you can design a Pelton wheel with any of these ratios, or, anything else as well, but it's typically optimal around a certain range. So one of these numbers is within that range and the others aren't. So you have to find out which one it is. Is it option A, 1 is to 12? Is it option B, 1 is to 22? Option C, 1 is to 2? Or is it option D, 1 is to 50? Okay, let's take a look at the solution. It's actually option A, 1 is to 12. So basically, the optimal ratio of this jet diameter to the wheel diameter of a Pelton wheel is somewhere around 1 is to 14 to 1 is to 16. So it's only option A that is close to that value, and the others aren't. So it should be option A. That's the correct answer. Okay, moving on. We'll move on to question number 5 now, which is asking us that which turbine operates as an axial flow reaction type with adjustable runner blades. So this question is a bit loaded. So it's an axial flow turbine, we know that much. It's a reaction type turbine as well, and the runner blades are adjustable in this type of a turbine. So which one is it? Is it option A, Pelton? Is it option B, Francis? Is it option C, Kaplan? Or is it option D, a propeller? So which type of a turbine operates as an axial flow reaction type with adjustable runner blades? Is it option A, Pelton turbine? Is it option B, Francis turbine? Is it option C, Kaplan turbine? Or is it option D, a propeller turbine? Okay, let's take a look at the solution. It's actually a Kaplan turbine. So um, the so we know that it's an axial flow as well as a reaction type turbine, and the runner blades are adjustable as well. So the only difference between a propeller and a Kaplan turbine, so between these two, is that the runner blades are not adjustable in case of a propeller turbine, whereas they are adjustable in case of a Kaplan turbine. All right, so let's move along. We'll move on to question number 6 now, which is asking us what is the primary reason for using guide vanes in reaction turbines? Is it to option A, ensure a proper angle of water flow? Is it option B, to increase the water flow velocity or speed? Is it option C, to reduce leakage losses? Or is it option D, both A and B? Okay, let's take a look at the solution. It's actually option D, both A and B. So the guide vanes in a reaction turbine, they serve really two purposes. One is to, to guide the water in the in the proper angle so that the entry angle in the main runner blades is correct. So that's the one of the reasons why guide vanes are used. And also they act like nozzles where the area of water flow is reduced along its path, and as a result the flow velocity of that water also increases. So they serve two purposes here, both A and B, and with that is why option D should be the correct answer. All right, let's move on. Let's move on to question number 7, which is asking us that the specific speed of a multi-jet Pelton turbine is given by what? Given that the number of jets being used are J and the usual definition of the turbine specific speed is given by Ns. Now, how would that get modified in when multiple jets are being used? Is it option A, Nsj equal to under root j into Ns, or is it nsj equal to ns by under root j, or is it option C, nsj equal to j into ns, or is it option D, none of the above? So when instead of one, multiple jets are used, so let's say I have a Pelton wheel like this with multiple buckets here. I have one nozzle working like this, another one like this. So in this figure I'm drawing four, but it could be multiple, even more as well. Sorry, this one would be like this, a nozzle here and a jet here. So, in this case, J equals 4, but you get the point, right? That there are multiple jets being used. So in that case, how would the specific speed uh, get modified? Given that, the unmodified specific speed was ns and the modified one is sj, how would these two be connected given that there are j jets coming into this turbine? Okay, so let's take a look at the solution. It's actually option A, nsj equal to square root of j into ns. So basically, for any given turbine, you can write the specific speed in this way, where n is the rotational speed, p is the power, and there's h below. Now, when there are instead of one jet, when there are j jets coming into this turbine, so then the power getting supplied as well as produced are both proportional to those number of jets, right? So we can write this modified equation in this way, where it's j into p divided by h5 by 4. So I just take the square root j out, and I'm left with the usual definition of specific speed. So therefore it's option A. So ns multiplied by square root of j. All right, let's take a look at the next question. So the Kaplan turbine can be thought of as multiple, uh, sorry, this should be reframed in a way that can be thought of, okay, as multiple types of which turbine. So it's like a single Kaplan turbine is equal to multiple types of which turbine. Is it option A, Francis turbine? Is it option B, turbo turbine? Is it option C, propeller turbine? Or is it option D, a Pelton turbine? Okay, let's take a look at the solution. It's actually option C, a propeller turbine, because both these are both axial flow reaction type turbines, whereas in the propeller turbine the blades are fixed, so the runner blades are fixed to the shaft or the hub. But in case of a Kaplan turbine, those blades can be uh, adjusted, and so therefore by adjusting those blade it can become different variants of a propeller turbine. So uh, we can think of one Kaplan turbine as multiple propeller turbines packed into one, where the blades can be adjusted and it can go from, you know, one variant of a propeller turbine to another variant, which is why option C should be the correct answer. Okay, so moving on, we'll move on to question number 9 now. which is asking us what is used to, sorry. So question number 9 is asking us what is used to regulate a Pelton turbine. Is it option A, a sphere and nozzle arrangement? Is it option B, a deflector? Is it option C, a brake nozzle? Or is it option D, all of the above? Okay, so now let's take a look at question number 10, where you have to match the following. So basically, and this is regarding the operation of multiple pumps at once, basically two of them at once. You can think of it that way. And there, how the operating characteristics change. So, this curve over here, this is a single pump, which is why it's marked by S, whereas these are the two other lines or curves. So one is this one, and two is this curve. And there are two different ways in which two pumps can be uh, used at once. They can either be in parallel or in series. So you have to match how does the operating characteristics change from S to 1 or 2 when we are using multiple such pumps, either in parallel or series. So there are really two combinations given in these options. It could be either A1, B2 or A2, B1. You have to select the correct one. Okay, let's take a look at the solution. It's actually option B, A to B1. So basically, when you are using, so let's look at this one by one. So when you're using multiple pumps in parallel, so then what happens is that the Q gets added, the volume flow rate, so it becomes Q plus Q2. As a result, the operating curve, it shifts to the right. It gets scaled horizontally. So, uh, V dot or Q, whatever you call it. And this is what happens in a parallel case. So 2 is basically parallel operation. And what happens in a series operation is that whatever pressure difference you create or the head you develop, that gets added. So H becomes the sum of H1 plus H2 in case you're using two of these. So in that case, the single operation curve, it gets scaled uh, vertically. So the whole curve moves up. And then you get this curve 1, this modified curve 1, which represents series operation. So it should be option B, which says parallel is 2 and 1 is series operation. Hope that's clear. That's all for this week. We will meet again next week. Thank you.